What specific problem does the proposed Cer-Eval method aim to solve in the evaluation process of large language models, LLMs, and how does it improve upon current static evaluation practices?
The proposed Cer-Eval method aims to address the limitations of the static evaluation process for large language models, LLMs, which simply reports average scores over entire test datasets without quantifying reliability or adapting to different evaluation scenarios. Cer-Eval improves upon this by providing a certifiable online evaluation framework that sequentially selects test points until a user-defined estimation error and confidence level are achieved, thus ensuring that the evaluation results are both accurate and reliable. It introduces the concept of test sample complexity, which quantifies the minimal number of test points needed for a confident conclusion, allowing for significant reductions in evaluation costs. By dynamically partitioning the input space into regions of low variance and high probability mass, Cer-Eval focuses on informative test points, thereby minimizing the number of samples required while maintaining evaluation accuracy. In practical applications, Cer-Eval has demonstrated the ability to achieve comparable evaluation accuracy using only a fraction of the test data compared to static methods, confirming its efficiency and adaptability.
How does the proposed Cer-Eval method work? Illustrate step by step, including details about its adaptive partitioning strategy and how it determines when to stop evaluating additional test points.
The proposed Cer-Eval method operates through a sequential online evaluation process that adapts to the model and dataset characteristics. First, it begins by partitioning the input space based on previously evaluated points, aiming to minimize uncertainty in each partition. This adaptive partitioning is achieved using a one-nearest-neighbor algorithm, which helps identify regions with lower variance and loss, thus focusing on informative test points. Next, Cer-Eval computes the sample mean and associated confidence interval, C, for each partition, allowing it to assess the uncertainty in model performance. The algorithm then selects the group contributing most to the overall uncertainty for further evaluation. This process continues until either the desired estimation error level is achieved or all available test points have been evaluated, ensuring that the evaluation is both efficient and reliable.
Can you provide a simple yet illustrative example demonstrating the inner workings of the Cer-Eval algorithm? Walk through the key steps using a hypothetical dataset.
To illustrate the Cer-Eval algorithm, consider a hypothetical dataset consisting of 1,000 multiple-choice questions across various difficulty levels. The key steps of Cer-Eval would unfold as follows. 1. Adaptive partitioning. Initially, Cer-Eval partitions the dataset based on the evaluated points, identifying groups of questions with similar performance characteristics. For instance, it might create partitions for easy, medium, and hard questions based on prior evaluations. 2. Estimation. For each partition, Cer-Eval computes the sample mean accuracy and the associated confidence interval, C, for the model's performance. If the easy questions show a high accuracy, while the hard ones show low accuracy, this variance informs the next steps. 3. Target group selection. Cer-Eval identifies the partition contributing most to uncertainty, which could be the hard questions due to their higher variance in performance. 4. New sample evaluation. The algorithm then selects a new question from the hard partition to evaluate. This targeted approach allows Cer-Eval to focus on areas where the model's performance is less certain, thereby refining the overall evaluation more efficiently. 5. Iteration. Steps 1 to 4 are repeated until the desired estimation error level is achieved or all points have been evaluated. For example, if the model's performance on the hard questions stabilizes, Cer-Eval may conclude that it has sufficient data to provide a reliable estimate of the model's overall performance. Through this process, Cer-Eval effectively minimizes the number of test points needed while ensuring a high level of confidence in the evaluation results, demonstrating its efficiency compared to static evaluation methods.
What are the theoretical or practical benefits of the Cer-Eval method over existing evaluation methods, particularly in terms of test sample complexity and evaluation reliability?
The Cer-Eval method offers significant theoretical and practical benefits over existing evaluation methods, particularly regarding test sample complexity and evaluation reliability. Theoretically, it introduces the concept of test sample complexity, which quantifies the minimal number of test points required to achieve a desired level of accuracy and confidence, thus providing formal guarantees on evaluation results. Practically, Cer-Eval adapts to the model and dataset by dynamically partitioning the input space, focusing on areas with higher uncertainty, which significantly reduces the number of samples needed, demonstrated by its ability to achieve comparable evaluation accuracy using only 5% of the test data in real-world benchmarks like MMLU and Alpaca-Val. Additionally, Cer-Eval ensures reliability by constructing confidence intervals that cover the true performance with high probability, addressing the shortcomings of static evaluation methods that lack such guarantees. Overall, Cer-Eval enhances evaluation efficiency while maintaining a controlled failure probability, making it a robust choice for LLM assessment.
How is the effectiveness of the Cer-Eval method validated in the paper, including the datasets used, experiments conducted, and the metrics for assessing its performance?
The effectiveness of the Cer-Eval method is validated through extensive experiments on both synthetic and real-world datasets, specifically the MMLU, Alpaca-Val, and math datasets. In the experiments, Cer-Eval is compared against two baseline methods, the static evaluation process, BASE, and a vanilla online evaluation process, SEEK. The evaluation metrics used include the average saving ratio, which indicates the proportion of test points saved compared to the BASE method, and the empirical failure probability, measuring the frequency at which the estimated performance falls outside the computed confidence interval. Results show that Cer-Eval significantly reduces the required test samples by up to 96% on MMLU and math, while maintaining a zero empirical failure probability across all datasets, confirming its reliability and efficiency. Additionally, the experiments highlight the importance of partition quality as Cer-Eval adapts to the model and dataset, leading to improved evaluation efficiency.
What limitations or drawbacks of the Cer-Eval method are mentioned, particularly in relation to its applicability across different LLMs or datasets?
The Cer-Eval method, while effective, has limitations regarding its adaptability across different LLMs and datasets. Specifically, the performance of Cer-Eval is highly dependent on the quality of the partitions it creates. If the partitioning does not accurately reflect the underlying data structure, the evaluation efficiency may be compromised. For instance, the method achieved significant savings in test samples for the math and MMLU datasets, but only modest reductions for the Alpaca-Val dataset, indicating variability in its effectiveness based on the dataset characteristics. Additionally, the empirical failure probability remains zero across all methods, but the need for more test points in certain datasets, like Alpaca-Val, suggests that Cer-Eval may require additional data collection to ensure accurate evaluations. This variability highlights the challenge of ensuring consistent performance across diverse LLMs and evaluation scenarios.